The equivalent representation of circuit elements. Those elements includes both active and the passive elements. Previously we have gone through the fundamental terms, classification of elements, Ohm's and Kirchhoff's law. So these particular will be used as well in defining the equivalent circuits. We have also gone through the source transformation, where say the practical voltage source is translated into the practical current source, or either way the practical current source can be translated into the practical voltage source. So these are the two equivalents, where say the practical voltage source is represented by a voltage source and a series resistance, where say the current source, practical current source is represented as a current source with a parallel resistance. This particular equivalence is also equally applicable when say there are say the dependent sources. So there is no additional trick, but the same logic has to be used here in transforming the dependent voltage source to a dependent current source equivalent likewise. We will be going for the equivalent representation, where say the series parallel combination of passive components will be discussed. Then we will also be discussing the series parallel equivalents of the active components, which includes the voltage sources and the current source. Third and the last, we will be discussing the star delta, or normally called as Y delta transformation for resistance. So this particular, you can say, is expected to be covered in this particular lecture with some support of numerical examples. So as say we have to go through for the series parallel configuration. So first understand what is the meaning of series connections. So when say the components are connected sequentially and consequently carry the same current, they are classified as the series connected elements. Important point is they are connected sequentially and carrying the same current. For the parallel connection, they are connected between the two nodes, or you can say the connected to the same nodes, and consequently have the same voltage across them. So basically you have identified a node pair, and whatever say the elements which are connected to those node pairs, they are regarded as the parallel connections. Now we are going to discuss, as suggested, the equivalent of passive component. So first we will be discussing for the resistance, then the analogous definition will be carried out for the inductance and the capacitance. In case of the resistance series equivalent, this particular is a arrangement where say the two resistors are shown. They are supplied by a voltage source, as suggested that when say the elements are connected in series, they are carrying the same current, so that is current I is common. As say the current is directed likewise, so the terminal to which the current is entering, that particular will be positive, so correspondingly V1 V2 are marked. These we have defined by the Ohm's law, they are combined, and on that particular basis the current is calculated as the voltage divided by sum of the two resistances. If you are calculating the V1 V2, which are say the voltage drop across the individual resistor, then that particular can be easily obtained because you are having the expression of current I. So when say V1 and V2, they are coming out to be totaling as the total Vs, supply voltage. So you can say they are acting as a voltage divider. So series connection is acting as a voltage divider because the voltage across the individual resistor depends on the numerical value of the resistance. So you can appropriately select the resistance value if needed. However, the equivalent resistance as experienced by the source is coming out to be the sum of these two resistances. The same arrangement has been extended to the general case where say the n resistances are connected in series. So the equivalent for that is the summation of all the resistances. And similarly you can calculate the voltage across the individual kth resistance, that is the Vs upon Req into Rk. The parallel equivalent of the resistance is shown likewise. So what we see that when say the elements are connected in parallel, the voltage across them will be the same. So whatever say the voltage is appearing across the R1, the same voltage is appearing across the R2. However, the current level is different, and that particular is decided by the resistance values. So the KCL suggests Is is equal to I1 plus I2, that particular is made clear here. This Is is expressed as Vs upon R equivalent, because we have to ultimately calculate the equivalent resistance value. Current I1 is Vs upon R1, current I2 is equal to Vs upon R2. So that summation is giving. So when you are comparing the dimensions, so 1 upon Req is equal to 1 upon R1 plus 1 upon R2. Now we have gone through previously that the reciprocal of the resistance is the conductance. So 1 upon R1 is the G1, and likewise the equivalent conductance for the parallel case is coming out to be sum of all the conductances. And on the similar line, the way we have defined the voltage division aspects for the series configuration, if you are calculating the current I1, I2, so they will be expressed like this. So in that particular sense, they are acting as a current divider. So what is the meaning of current divider? That if suppose say the two resistances are there, they will be carrying the current and their sum will be equal to the Is. So there is a division of current which is taking place between the resistances. This particular has been extended to the general case. So the Is is equal to sum of all the currents. When you are comparing the dimensions likewise, so it is giving you the equivalent conductance as the sum of all the conductances connected to that parallel nodes, and this particular is a expression of current division. Now the important aspects which we used to encounter, that what will be happening if suppose say one of the resistance is either getting shorted or let us say it is open circuited. So normally when say sometimes the switching problem is there, let us say there is a switch, when say it is a short circuit, so it is a closed switch, when say it is open, so it is a open switch. So that short circuit is represented by the zero equivalent resistance. So R2 is taken as 0. What will be happening? We will be analyzing. So I2 in this particular case is there, and that particular value will be equal to the Is, where say the current drawn by this I1 will be 0. So during the short circuit, the short circuited branch is carrying all the current, where say the other elements which are connected in parallel will be carrying the 0 current. During the open circuit, which is represented by an infinite resistance, so the current to that open circuit element will be 0, where say other will be sharing the currents. So in this particular case only one resistance is there, so that will be carrying whole of the current Is. Now the series parallel equivalent has to be worked out, and we have to make use of in finding out the simplified representation or the equivalence of the circuits. So this particular is an example which is taken here. Here say the purpose is to find out the RAB equivalent resistance experienced at this particular terminal because of this interconnected arrangement of the resistance. So we have to have a careful look and find out the series parallel combination first. So in this what has been observed, that this 20 ohm and 5 ohm, these two resistances are connected in parallel. This particular 18 ohm and the 9 ohm resistances are connected in parallel. This particular is basically the same terminal, there is no element present, it is only a connecting wire. So we will not be counting that any element is present over here. So because of these two parallel equivalents, you have calculated the resistances and demonstrated how the equivalents look like. So 20 and 5 parallel is resulting into the 4 ohm value, where say 18 and 9 ohm they are resulting into the 6 ohm. So now this particular circuit is looking little simplified. Now next what we will be seeing, that this 4 ohm and 1 ohm resistance they are connected in series. So that particular is resulting into the 5 ohm. This is connected in parallel with this 20 ohm. So 5 and 20, they are again making to be equal to the 4 ohm resistance. This particular will be the equivalent translation, and 4 and 2, they are coming out in series. They are in parallel with this 6 ohm resistance. So ultimately you are able to calculate the net resistance between the two terminal by say successively reduction or simplifying the circuit by the series parallel arrangements. Now on the analogous line we will be making use of the equivalence of the inductance and the capacitance. Only equation which we have to recollect for the inductor, that the voltage across the inductor depends on the inductance value L and the derivative of the current. So if suppose we are spelling out V1, it is L1 di upon dt, because the I1 is equal to I2 is equal to IN, so currents are common. So because of this the equation is translated like this, and ultimately we will be having the same expressions as corresponding to the case of resistance. So the equivalent inductance in this case is the sum of all the series inductances likewise. Here say they are connected in parallel. So likewise in parallel case the current division is taking place. You can proceed on the similar line. Likewise you are having say the KCL equation Is is equal to I1 plus I2 plus I3. You have done the derivative of this. Corresponding to the derivative, this di1 upon dt is represented as Vs upon L1. So on that particular basis you will be finding out the expression for the equivalent inductance. 1 upon L Eq is equal to 1 upon L1 plus 1 upon L2 plus up to 1 upon Ln. Now this is a capacitor case. So again in case of series arrangement there is a voltage division taking place, and because of the voltage of all, the sum of all the voltages is counterbalanced by the supply voltage. So that particular is the KVL relationship. You have substituted the expression I is equal to C dV by dt for capacitor. So correspondingly when say the current is equal, you can calculate the individual dV1 upon dt components, dV2 upon dt, likewise dVi upon dt, dVn upon dt, and when you are rearranging you will be getting the expressions like this. So there should not be confusion by the expression, because you cannot make a correlation. Here again the concept is, in case of series the voltage division is taking place, and 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2 up to 1 upon Cn. In case of parallel arrangement the current division is taking place, that relation is dictated by the KCL, and you will be ultimately ending up with the simplified expression where say the equivalent capacitance is sum of all the capacitors connected in parallel. Now we are going to have a discussion on the equivalence of the active components. So in this particular case the voltage sources and the current sources are treated in one by one manner. In case of these two sources, first I will be considering the ideal sources, then there will be arrangement for the practical sources as well. Now this particular is a case of ideal independent voltage sources when say connected in series or in parallel. You can easily see that when say the source is there, so it will be specifying a voltage because it is a ideal voltage. So V1, V2, Vn they are specified. Now the equation suggests that V equivalent is equal to VAB, that is the sum of all the voltages as per the KVL. So this is simply represented by a simplified two terminal source where say the voltage level is now V1 plus V2 plus up to Vn, or sum of all the voltages. Now when say they are connected in parallel, so one overriding consideration in this, that the voltages has to be equal. So when you are saying the voltages are to be equal, their magnitude has to be equal, the polarity has to be equal. So this particular is the restriction imposed by the KVL. However, the equivalent voltage will be, when say the voltage level are equal, so it will be by any of the source value. One important point here, see, although the voltage level is coming out to be corresponding to the individual one, but the current supplied by the other one can be different. So they will be sharing the current and so on. Now this is a practical voltage source. So previously we have seen that a practical voltage source is represented by a ideal source and a series resistance. So this particular is first source, this particular is second source, third source, likewise. What we have seen, as if suppose say correlating with the previous discussion, the voltage sources are to be added, so that particular is giving rise to the E equivalent, and all the resistances are coming out to be in series, so that is forming the series equivalent. So this particular is a simplified two terminal equivalent of a series connected voltage source. Now these are say the practical voltage source connected in parallel. So when say previously we discussed, we have seen that the terminal voltage has to be identical. However, when say they are of practical nature, each of the source is having a resistance. That internal resistance is participating in series. So because of this, if suppose say any imbalance, there will be a circulating current sector, that particular can be taken care of. However, at this point of time, when say there is a voltage source, there is a series resistance, so this particular can be represented by an equivalent current source and the parallel resistance, where say the current source value is equal to the voltage source value divided by the internal resistance. So this particular is corresponding to the first source, this particular is the equivalent corresponding to the second voltage source, this particular is consideration for the nth practical voltage source. Now what we are seeing, the currents are coming out to be added, because in parallel the current source they can be added. So that particular is forming the I equivalent, and you are simply substituting the values. So the I equivalent will be E1 upon R1 plus E2 upon R2, likewise up to En upon Rn, where these particular resistances are now participating in parallel. So whatever say the parallel equivalent, what we have seen, in case of parallel, the total conductance or the equivalent conductance is the sum of all the conductances. So G1 plus G2 plus up to Gn, that is forming the G equivalent. The reciprocal of the conductance is the resistance, so that resistance value is calculated, and ultimately we can translate this into a practical equivalent voltage source. So that is EEQ and REQ, and how this particular is to be calculated, so that particular procedure is listed out. Now in this particular case of the current sources, so when say the sources are of, let's say sources are connected in series first, I1, I2, I3. So in series the current will be 1, that will be common to all. So there is a restriction, and that restriction suggests the connection is possible only when I1, I2, I3 up to In are identical. So when say they are identical, this particular is represented by this equivalent arrangement. In case of parallel, So there is no restrictions as such, and equivalent current source can be obtained while combining, or you can say adding, all the individual current sources value, because they are connected in parallel. Now analogous line discussion has to be carried out while say we are finding out the equivalent of number of series connected current sources. So an individual current source of practical nature is represented by a ideal current source and the parallel resistance. So this particular representation is done. So this is first source, the similar representation for the second source, similar representation for the nth source. Now what we can do, we can form the equivalent voltage source representation by of, you can say, this current source. So that particular is giving rise to the value. However, E1 is to be corresponding to the I1 R1. So in this way you are able to represent the series connected current sources to the equivalent voltage sources. What we have seen previously, that E1, E2 up to En, they can be added to form the equivalent, so that is E equivalent is obtained. Resistances are coming out to be in series, so R equivalent is obtained. And once this particular is done, you can find out the equivalent voltage source. Likewise, correspondingly, we have to have the practical current source equivalents, so that particular is done. How they are related? I equivalent is equal to E equivalent upon R equivalent. Likewise. Now practical current sources, when connected in parallel, the representation will sound like this. We have already seen, when say the number of current sources are connected in parallel, they will simply be added. So that particular is forming the I equivalent. R1, R2 up to Rn, these are the resistances connected in parallel. So we have to approach the conductance formulation, find out the conductance equivalent. G equivalent is equal to G1 plus G2 up to Gn, and attempt the reciprocal. So that particular is forming the R equivalent. Likewise. Now this particular we have gone through for the series parallel combination for the resistance, inductance, capacitance, voltage sources, current sources, likewise of both ideal and the practical nature. Now as we have seen that the series parallel transformation can reduce the complexity of the circuit. If suppose say we have to find out the equivalent resistance, and we can calculate what amount of the current is to be extracted from the supply voltage if connected across the terminal under consideration. So this is another way of you can say another method when say the complicated circuit is represented likewise. So we have to go for the transformation. Here say these particular images are superimposed. So whatever say shown on the black lines, that is forming the delta. Whatever say with the blue, that particular is forming the star. So ultimately the purpose is we have to relate this Rx, Ry, Rz in terms of Rxy, Ryz and Rzx, or the either way. So that is why we will be going for the transformation. That particular is regarded as a star delta transformation or delta star transformation. It will be more clear while say we are separating these particular two circuits. So this is the star arrangement, this is a corresponding delta arrangement. When say we are saying the equivalence, that means if suppose say simply looking from these particular terminal viewpoint x, y, z, the behavior will be identical. So ultimately it is, you can say, the equivalent representation that we are interested in working. Now let us consider the two terminal Y and Z under consideration. Third terminal is left open circuited. So what will be the resistance experienced by the star arrangement, and what will be the resistance experienced by the delta arrangement? So this particular R by Z corresponding to the star, it will be Ry plus Rz. That particular is mentioned. Whereas when say you are simply looking to the Y and Z terminal, third is not connected. So what is we are seeing? Rxy and Rzx, they are in series. This series combination is in parallel with the Ryz. So that particular is formed. These are, you can say, simply you have used the expression of the parallel connected resistors. So that particular is done. On the similar line, you repeated the procedure for other two combination of the terminal. Here say we considered earlier the YZ, so you can say ZX are the consideration, then XY are the two terminals, and you have obtained the three such equation 1, 2 and 3. When say you are adding these particular three equations and dividing them by the 2, you will be ending up with the Rx plus Ry plus Rz on the left hand side, where say this particular expression on the right hand. What is happening if suppose you are simply adding, that twice of the term will be appearing, like say here say the 6 resistances, so they will be adding up 2 of Rx plus 2 Ry plus 2 Rz. So similarly on this particular, that's why it is needed to be divided by 2. Now the next step is, when say we have to separate, we have to express this star resistances in terms of the delta parameters. So from this fourth equation, if suppose say I am subtracting the first equation, we will be ending up with the expression of Rx. So that particular is done. So as a summary, the equation number 1 and equation number 4 are represented. We have subtracted, so the Rx is obtained likewise, and correspondingly you can obtain the 4 minus 2, 4 minus 3, so Ry and Rz expressions. You recollect these particular terms, have a look. So what this Rx is spelled out, if you are looking to the terminals representation, then this particular will be the Rx you are looking for. This particular Rxy and Rzx, they are coming out to be the adjacent resistors. So on that particular basis, you can have a word statement that each resistance in the star is equal to the product of the two adjacent delta resistances divided by sum of all three delta resistances. So this is how you can remember the transformation. Now we have, on that basis you can say, calculated Rx, Ry, Rz. Now our intention is to express the Rxy or R by Z, Rzx, the delta resistances in terms of the star resistances. So these are the three equations. You are taking two at a time and multiplying all combinations. So Rx, Ry, Ry, Rz, Rz, Rx. So that particular is resulted on the left hand side. Correspondingly, there will be a term on the right hand side, and you have rearranged. So there is a term common between the numerator and the denominator, and that common term will be Rxy plus Ryz plus Rzx. So that common term is cancelled, and here say ultimately what what is left. So that particular is Rxy, Ryz, Rzx upon sum of the three. So here say the product of the three, and this particular is sum of the three resistances. Now here you can easily make a comparison that what basically we calculated. So this particular is coming out to be Rxy, which is a separate term, and we calculated previously the RZ, because that was a product of the two adjacent delta resistances divided by sum of the three delta resistances. So that is substituted. Now RZ, we are dividing whole of the expression by the RZ, so you will be ending up with the RXY. So what it is giving us, you see the numerator, it is a product of, or you can say sum of all possible product of the star resistances divided by opposite star resistance. So that is how you can spell out. On this particular basis, the statement each delta resistance is sum of all possible products of the star resistances taken two at a time and divided by opposite delta resistance. The same expression can be written into the different form. So this is by dividing it. So Rxy is coming out to be Rx plus Ry plus Rxry upon Rz. So this you can recollect easily. Rxy is, you can say, the delta resistance between the two terminals X and Y. So that is equal to sum of the two star resistances, or sum of the resistances touching these two terminals plus their product divided by the third or the opposite resistance, like that. So this is how we have to have, and sometimes it is not possible to simplify the network by only the series parallel combinations. We may require this star delta transformation as well. So this is also to simplify the circuits. Now take this particular as an example. Where say we are expressing in terms of, when say it is a balanced arrangement, all three resistances are equal. So the intention is find out the equivalent delta resistance when say the star resistance is given, or find out the equivalent star resistance when say the delta resistance is given. So in this consideration, let's say the star resistances are equal. What will be the corresponding delta resistance? So corresponding to the delta resistance, we know the expression Rx y is equal to Rx plus Ry plus their product Rx Ry upon Rz. All three resistances are equal. So this is R, this is also contributing R. So Rxy is coming out to be 3R, or this R can be corresponding to the, R is corresponding to the star arrangement. So that particular R delta is coming out to be 3 times the star resistance value. And similarly, this, or you can say analogously or correspondingly, you can write R star is equal to R delta upon 3. So one interpretation which has gone in why the delta resistance values are coming out to be higher, where say the star resistance values are coming out to be lower. So it is the interpretation that for the star, the arrangement is like they are connected in series when say you are simply considering the two terminals. Whereas in case of the delta, when say the two terminals are under consideration, it is because of the parallel combination and so on. So that is the reason behind to have a lower value of the star resistances and the larger value of delta resistances. Now take one example where say we are interested in finding out the RAB first and the current I. So you have a careful look that we cannot solve this particular simple circuit by the star delta combination. We cannot obtain the R equivalent RAB by the series parallel combinations. So on this you have identified, let's say, this 20, 10 and 50. they are forming the star. Another star you can identify likewise this, 20, 24, 30 and so on. You can identify 24, 20, 10 as a delta connected arrangement. You can also identify 20, 50, 30 as another delta. So in either way we have to approach. Let's say I am considering that 10 ohm, 50 ohm and 20 ohm are forming the star, and corresponding we will be translating the star to the delta. So whatever say the for the original circuit elements, they are shown with the dotted line, that we are going for the equivalent representation. And here say the values are calculated. So corresponding to say this R1, what has to be the sum of this resistance and this resistance plus their product divided by the third one. So on that basis you have calculated R1 is coming out to be 34 ohm, R2 is 170 and R3 is 85. In the next slide I am re-representing this. So what you will be seeing that this 24 and 34, they are coming out to be in parallel. 30 and 170 are in parallel. Here say it is only a re-representation of the same node. It is not a circuit element. So they are connected in parallel. That parallel combination is there. Now these two resistances are coming out to be in series, and that series combination is in parallel with the 85 ohm resistor. So that particular is worked out, and ultimately this particular resultant will be in series with the 13 ohm resistor. So that's why the RAV is calculated likewise, and this is coming out to be exactly 40 ohm. Once the RAV is calculated, you can calculate the current drawn as requested in the question. So that particular is 100, which is the supply voltage, divided by the equivalent resistance 40, so 2.5 for the today's discussion. Next I will be putting the summary. So passive series circuits act as a voltage divider that we have seen for the resistance, inductance, capacitance. Passive parallel circuits act as a current divider, so there is no point to argue, this is already clear. The ideal voltage source can be connected in parallel only when say their terminal voltages are of equal magnitude and polarity. So this is a restriction because of the KVL you can associate. On the similar line, ideal current sources can be connected in series only when say the current levels are of equal magnitude and polarity. So this is a restriction because of the KCL. What we have seen previously, that the practical source combination can be represented as a single equivalent using the source transformation, but please be mindful that this particular equivalence can be formed only for the practical sources, where say they are represented by the ideal source and a resistance combination. The appropriate choice of the transformation is useful in working out the equivalent circuits, equivalent resistance, but the appropriate choice will come with the practice. Next, we will be discussing the methods of analysis, that includes the nodal method of analysis and the mass method of analysis. For further reading, you can refer these particular text. Thanks.